restricted to omega k, it's given by this in the basis by this 2 by 2 matrix. Okay, so it's a bijection, so it's piecewise linear, and I might so I will give I will need to spend about half an hour, half of the talk, just explaining the motivation and kind of like the background to how we get to study this map. And so I'll keep this part of the board stay there. If you doze off during the history, I could recommend that you think about this map. And I'll tell you we know a lot of things about this. So I should say this is a piecewise linear bijection. This not hard to check. And I'll make some other observations, namely that if you take T of omega k, this is the reflection of omega k in the line y equals x. And I'll illustrate that if you took, this is omega k, this gets mapped to a little piece over here, which is kind of like the reflection. Okay, so you can imagine all the small pieces here, all of them are mapped over, and they line up in this corner, and this is the map, and this defines a dynamical system. Another fact, which maybe I won't write here, there's not enough space, but the inverse map is conjugate to the map itself, and it's conjugated by the reflection in the line y equals x. So those are all the facts about this dynamical system are relatively easy to check, but there are many such facts. And so I'll begin by explaining kind of like why people were interested in this. So this was introduced in 2000, around 2000, by Boca, C.Cobeli and Zaharescu. And actually, there were two papers. There's one in 2000 and one in 2001. And in 2000, they were looking at, say take the integer square lattice, and you take all the points in here, and you look at all the angles that you can get between, you order them all by angle. So there's a finite number of angles that you get, and you want to know what's the distribution of these angles. That's what they were studying. And it's a natural question from physics point of view. And so this is called the gap distribution. And they were able to figure this out. And it turns out that this gap distribution was already introduced or discovered by Hall in 1970. Although Hall was studying a different problem. Hall was studying the statistics of Farey fraction. And so in the study of Farey fractions, Hall introduced, he studied, I'll just keep it very brief here, he studied the second moments of higher order gaps. So you might not take the first gap, but you might skip a few. And he was doing this for Farey fractions. And studying the asymptotics. So he conjectured in a paper in 1994 that you can look at the asymptotics involves a polynomial in the order, the higher order gaps h. And so this polynomial has coefficients. He conjectured there are these coefficients, and he computed the coefficients in two cases, like h equals 1 and h equals 2. And the h equals 1 case is kind of in his first paper. And so this is, so I'm not giving you the details here, but I'm just explaining that there was a conjecture. And in the 2001 paper of Boca, C.Cobeli, and Zaharescu, they prove Hall's conjecture. They write down what the coefficients should be. And these coefficients are expressed as integrals over this triangle of a very natural function that shows up. And so that's the first time this dynamical system appears. Okay, so if you've read the abstract, there's a connection of this to Riemann hypothesis. So that's what I'll explain next. Here I'll have to go a little further back. So in 1912, Littlewood showed that the Riemann hypothesis is equivalent to this sum Mobius function being O of n to the 1/2 plus epsilon. Okay, so the Mobius function of a positive integer, E1, is just the parity of the number of distinct primes and 0 if it's not square free. So Riemann hypothesis has a reformulation or complete characterization in terms of the Mobius function. This is quite well known. Later, Franel gave another characterization in terms of Farey sequences. And in the same journal, but after Franel's paper, there's a paper by Landau, which gives another characterization of Riemann hypothesis. And I'm going to write down Landau's first. So Landau says, we take the Farey sequence of level n. Let me just explain here. A of n is the sum of Euler phi functions, and it's the number of elements in the half-open interval, unit interval, number of rationals of denominator at most n. Okay, and so we number these rationals. P0 over Q0 will be 0, and then P1 over Q1, this will be 1 over n. And then you just order all of them. PAN, QAN, 1. And the result of Landau is that if you compare these Farey fractions to the uniform distribution, and this being the sum over all of the terms, being n to the 1/2 plus epsilon, this is equivalent to Riemann hypothesis. Both of these papers are actually very short. It's only like 3 or 4 pages, and they build on the paper of Littlewood. The result of Franel is to do an L2. In this case, this is O of n to the minus 1 plus epsilon. I'm sorry that my... Okay. All right. So there we have Franel and Landau, the two characterizations of Riemann hypothesis. So it turns out that there's a bit more. Franel's paper received more attention than Landau's paper, if you look at the citations. And I would say part of the reason is because people prefer kind of like doing L2 second moments. You get rid of the absolute value sign, okay? And so it's more easy to analyze if you want to do computations. But the characterization of Riemann hypothesis that we will be using is the Landau version. And so you say, well, if you want to attack Riemann hypothesis, you would need to study how this expression here behaves, okay? And I don't see anybody trying to do that directly. At least I'm not sure if I'm missing something from the literature. But so far as I can tell, the first time that people kind of move in this direction was by the paper of Hall, as I mentioned earlier, in 1970. And so what Hall does, he says, well, okay, maybe this is not easy to analyze, but maybe instead you look at the Farey statistics. Maybe you look at Pj over Qj minus Pj minus 1 over Qj minus 1. These are called Farey gaps. So you look at the absolute value of that. I mean, if you want to study something like this, maybe this is like a similar looking problem. And this is nice because if you know about Farey fractions, you know that consecutive Farey fractions are unimodular in the sense that the cross product here is equal to 1. And so you get rid of the absolute value that way too. And this is also not hard to analyze. And in particular, this is always bigger than 1 over n squared. And the distribution of these, so that we have like an such numbers. For each n, there are an such numbers. And you look at the distribution of such numbers. You kind of want to rescale by n squared. So you take this gap and you scale it up by n squared. That's the distribution that looks like something like this. There's a lower bound of 1 because of this inequality. And it has some kind of a mean. The mean is pi squared over 3, which is the limit of n squared over an as n goes to infinity. And it has this, I'll call it a quadratic tail. So the variance is infinite. So it doesn't have a second moment, but it has all p moments for p less than 2. Okay, so it's just quadratic here is critical. That's what I'm saying. So the key is that this is the second moment doesn't exist, but in a critical way. And when you look at the collection of an numbers, the distribution, and you look at the variance, that's a finite set. And so the variance of this finite set, call it mu sub n, this will go to infinity. But it doesn't go to infinity as a polynomial because the variance is like the second moment. So it goes to infinity like log of n. And so roughly it's log of n, but you could actually like figure out what these there's like an asymptotic expansion. This is what I'm going back and telling you about Hall's conjecture that kind of started looking at the asymptotics here. So I would say most likely the BCZ map was already implicit in the work of Hall, but he didn't write it down in the paper. But certainly the background. Now I'm spending a lot of time on the background because I think if you want to attack the Riemann hypothesis, you should know what other people have tried and what they might not have tried. Okay. So understanding the history is going to be important. Okay, so as I said, Boca, Cobeli, Zaharescu in 2001, they proved this conjecture of Hall in his 1994 paper, and they used the BCZ map to answer not just that conjecture, but they also wrote a few other papers where this was used in a systematic way. And so they started asking, this is the question of Boca, Cobeli, and Zaharescu. They asked, is this map, so now this is the map, piecewise linear bijection of a triangle to itself. They start asking dynamics questions about this map, okay? They say, is this map ergodic? It's not clear, okay? It's measure preserving. Lebesgue measure is obviously preserved, okay? It's measure preserving. What else can you say? You can find some periodic orbits. One thing that I challenge you to do is to find all the periodic orbits. That's maybe not so easy. But the questions they ask is, what is its entropy? You can measure the entropy of this map. And is it mixing? So this is around 2000, maybe 2004 or something like that. And now I want to turn to dynamics, okay? And I want to explain a little bit how we got involved in studying this. So in dynamics, our goal is to understand all orbits of a dynamical system. But usually that's hopeless, okay? In other words, if you ask the question, can you understand all the orbits? That's like a bad question. You should not ask that question because it's hopeless, okay? It's hopeless even if you restrict to your attention to just looking for periodic orbits. So I'll give you some examples of why this might be a bad question. Example 1, irrational rotations. In this case, there are no periodic orbits, okay? My second example, this is what's sometimes called the cat map. Of the torus to itself. Okay, this is an example of a Nosov map or a very chaotic map. Here, there are lots of periodic orbits. And we can even say something about the growth rate of the number of periodic orbits as you order them by length. But if you ask, can you classify all these orbits? Have you seen every periodic orbit of the cat map? That's another bad question. We don't know if there's a nice answer to such a question. But now I'm going to give you the third example. This is the Gauss map. The Gauss map is even more chaotic. However, if you ask for the periodic orbits, there's a nice answer. Okay, periodic orbits is just periodic continued fractions. These are you can construct all of them, and these are in one-to-one correspondence with ideals in quadratic orders, real quadratic orders. So some number theory stuff. And these are in one-to-one correspondence with closed geodesics on the modular surface. Okay, I'm running out of space there. But somehow this one is very interesting. We can understand all the periodic orbits. Now, I want to say that I want to say a bit more about why about this. What's special about the third example? So this Gauss map, it arises as a Poincare section of the geodesic flow on the modular surface. Okay, and in fact, so the modular surface is like the unit tangent bundle. We can write it as SL2R mod SO2. We can write it as a double coset space mod SL2Z. And if you don't mod out by SO2, you can think of that as the unit tangent bundle of the modular surface. And here, the famous Gauss measure on the unit interval, this is like the push forward of Haar measure. So there's a very natural explanation for where the Gauss measure shows up. Okay? Now, my fourth example is BCZ. It's this map that I put on the board. This is a Poincare section of the horocycle flow. If you don't know what horocycle flow is, don't worry. I'm not going to use it. But it's kind of like a partner to the geodesic flow. Geodesic flow is an example of hyperbolic dynamics that's very chaotic. And the horocycle flow is a very special kind of flow which was discovered by studying Anosov flows. And with Athreya and myself, we discovered that this is the BCZ map is a Poincare section of the horocycle flow, and in particular, the Hall's distribution is the push forward. So the Lebesgue measure on this triangle is induced by Haar measure. And Haar measure, if you push it forward under push forward of Lebesgue measure on the BCZ triangle under this roof function, we call it R. R is the function on this triangle, which is 1 over AB. So when you do a Poincare section, you take a transversal and you wait till the first time you return to this transversal. This is called the return time, or the roof function. And so this function you can show, well, I haven't told you how this is a Poincare section, but there's a way to embed this triangle into the unit tangent bundle such that this becomes the roof function. It's a very natural way. In fact, Athreya and myself, we rediscovered the BCZ map. We did not know about the BCZ map when we were investigating this. We knew about this fact here, and we were thinking, oh, how nice it would be to develop the theory if we replace the dynamics with the horocycle flow. So that's kind of our motivation. And when we did that, we came up with this map. And then we were very lucky that Jayadev Athreya was starting his assistant professorship at UIUC, where Boca and Zaharescu were both there, and they immediately connected. Okay. So I will also like to say here that there's an important class of parabolic dynamics of which the BCZ map or the horocycle flow belongs to. So there's hyperbolic dynamics, there's elliptic dynamics, but on the boundary between the two, there's something called parabolic dynamics. And for parabolic dynamics, it's reasonable to hope to understand all orbits. And so this is many of you have heard of the work of Eskin Mirzakhani and many others on the SL2R action on SL2R orbits. I won't say what it is. And those are the situations where it is reasonable to hope. Now, to actually classify is another problem. That will involve a lot of work. But it's reasonable to expect that it can be done if one really wanted to. Okay. Now, so this, the discovery of this kind of parabolic dynamics really began with the horocycle flow. And I will state one theorem which goes back to the 70s and 80s. This is Furstenberg, Dani, and Dani Smiley. Something like that. Horocycle orbits on a finite volume complete hyperbolic surface are either closed or equidistribute with respect to R. Moreover, there exists a one-parameter family of closed horocycles for each cusp. Okay. So, as a corollary to this fact is that if we take this BCZ map, this piecewise linear bijection, every periodic orbit, we can find all of the periodic orbits it's of this form. So I'll give you the standard periodic orbit. That's the periodic orbit. It's right there. Maybe I'll make it red here's the point 1 over n comma 1. If you take that point and you iterate it under the BCZ, it will come back to this point after an steps. And so this is a periodic orbit, and the period is an. And if you multiply this by a real scalar, this will remain periodic. So this is a linear map. It's piecewise linear. And you can easily see that this remains a periodic orbit. And in particular, the only admissible periods are these a sub n's, where a sub n is the sum of these Euler-Phi functions. Okay, so this fact here is not hard to prove. One can prove it without using this theorem, but for us to discover it first, we discovered it using the theorem. I will let me remark. I think there are a couple of relevant remarks. So there's a well-known result of Sarnak, which says that Riemann hypothesis is equivalent to some rate of equidistribution of closed horocycles. There's a one-parameter family, and these horocycles get longer and longer, and as the length goes to infinity, it equidistributes with respect to r, and you can measure the rate of equidistribution in some representation theory sense, involving Sobolev spaces, and the rate at which these things converge. Another important relevant result is that it's in the thesis of Andreas Strombergson, which says that actually, if you take a closed horocycle, the standard notation for this is here's the modular surface, and a horocycle at height y could be less than 1, but it's kind of wrapping around. This one parameter family is parameterized by a positive y, but you can take a piece of this horocycle, it's maybe just a small piece, like this piece from alpha to beta, and the difference beta minus alpha can be going to 0, but if it goes to 0 slower than this rate, or slower than this rate, this lower bound here, then it still equidistributes. Okay, so this is a sufficient condition for equidistribution. However, this is not a rate condition, and nobody has tried to relate this fact here to maybe the rate of equidistribution. And that's kind of, I asked Strombergson, and he doesn't know anyone trying to do that, which is surprising. I should also mention we also don't know anybody who has tried to use these kinds of results to prove things like prime number theorem. So prime number theorem is not known using dynamics, so far as I understand. Okay, so I think I'm more or less done with the history, or at least most of it. I'll mention here, just to make the connection between BCZ and Farey fractions more clear, that the ith point here, you can write it down. It's qi over n, qi plus 1 over n. These are the denominators of the Farey fractions. And so you can see the BCZ map is just kind of enumerating the Farey sequence in order. And now I'm going to go back to the formulation of how we're going to reformulate the Riemann hypothesis in terms of dynamics. So I'll begin with Landau. I'm going to take the Landau formula, multiply it by this n squared over an, which doesn't really change anything because that's approaching a constant. And so we conclude that the Riemann hypothesis is equivalent to, so I'm going to take the expression in Landau and in the sum end of the expression for Landau, and write it as a telescoping sum. So it becomes something like this: n squared over qi minus 1 minus n squared over an. N squared over an is converging to pi squared over 3. That's a convenient thing to know. So this being O of n to the 1/2 plus epsilon. This sounds like an analysis problem. Okay, you just have this sequence of numbers and you need to get some bound on it, and that is Riemann hypothesis. Well, what I did here is I factored out an so that I want to look at the expression in Landau as like an average. And now I want to bring in this dynamical system. So I have this, let me call R sub n. R sub n is my roof function. Roof function is R, or it's just 1 over AB minus this n squared over an. This is the thing that I call the BZZ cocycle. The cocycle is just a function on this triangle. It's a sequence of functions. Okay, so cocycles. And so I'm going to rewrite this in terms of these BCZ cocycles, the Rn. So this becomes 1 over an sum j equals 1 up to an of sum from I equals 1 up to j of Rn t to the I minus 1, 1 over n1. So I take this periodic orbit, this thing being O of n to the 1/2 plus epsilon is equivalent to Riemann hypothesis. So I'm taking the average of some partial sums of the values of some function along the nth periodic orbit. This is taking the Landau formulation, characterization of Riemann hypothesis, and just rewriting it in terms of this dynamical system. So we haven't done much. So this is, let me call this star. Okay, this formulation of the Riemann hypothesis. Okay, in a word about the terminology cocycle, just to sound cool. The reason we call this a cocycle is because the term cocycles is usually used when we study dynamics on vector bundles. So for example, if you have a smooth diffeomorphism it induces a dynamical system on the tangent bundle. And when you deal with that, you have to multiply, you have to compose the derivatives along an orbit. So it's a multiplicative cocycle where you multiply matrices along the orbit. So here we have our BCZ cocycle is like, you should think of it as it's a cocycle for a line bundle. And so it's an abelian cocycle. There's no, we're not dealing with matrices. And so I'm using addition notation, and so instead of multiplication, it becomes summation. So I'm doing partial sum. So the language of cocycles is motivated by this kind of analogy. Okay? And the thing that we're summing, the generator of the cocycle is this function. And so we're taking sums of this function along orbits of BCZ. Now, why is the Riemann hypothesis hard? My next thing to explain. So I want to look at this expression, and I want to think of it as like I give you a random walk perspective. We usually try to, when we have something that we don't understand, we assume it's random, and then we try to guess what can we expect. Okay, so so here the generator. I should tell you that this is a fact that Rn, this BCZ cocycle, has mean zero along this periodic orbit. Okay, and so we're taking, we have like a random walk on the real line where we're moving according to this function, to the left or to the right, and what we can think of is this, the left-hand side or the right-hand side of this equivalence is the average displacement of a random walk. The average displacement of the random walk being equivalent to being O of n to the 1/2 plus epsilon. So you might say, oh, this is just square root cancellation. Hold on. Okay, this is not square root cancellation because an is roughly like n squared. Okay, an over n squared converges to a constant. So square root cancellation would be like O of n, and O of n is not even enough to prove prime number theorem. To get prime number theorem, you really need little O of n. Okay, so if you only have your usual square root cancellation that you expect, you're not even going to prove the prime number theorem. So in order to prove the Riemann hypothesis, if you're going to try to do that, you have to explain where are you getting all that extra cancellation. Okay, and there are actually quite a few things that we know. I think I skipped something in my notes. Right. I didn't tell you that we had 3 questions. The ergodicity, this is for free. I got with Athreya and Cheung because we know the connection to horocycles. So we also established entropy 0. And the mixing question is still open. But with Anthony Quas, we showed that the BCZ map is weakly mixing. And the proof of weakly mixing uses a very nice property which we call infinitesimal self-similarity. And it's an amazing fact, which I'll describe very quickly. If you take this map here and you cut out a smaller triangle here and you do first retime to this smaller triangle, you're going to get a very complicated map. However, that map is conjugate to the original BCZ map. And that's like unbelievable, but you prove it in a couple lines. I should maybe say that our methods of proof is, I don't know if you can call this a method, but I refer to it as dynamics on moduli spaces, where you get used to thinking about objects. For example, on the modular surface, you may have a unit vector, but this space is also SL2R mod SL2Z. And so instead of thinking of the objects in the unit tangent bundle as unit vectors, you think of them as lattices, which are more richer geometric objects. And once you see all the dictionary, then a lot of these facts become easy to check. Okay, so I've explained the background. Now I need to explain. I only have maybe 15 minutes, 10 minutes. The new result, the thesis of Yiming Li. So I was explaining here that the Riemann hypothesis is equivalent to saying that this average displacement of the random walk generated by these BCZ cocycles along periodic orbits being O of n to the 1/2 plus epsilon. So now let K transpose so K is this integer value function. It's 1 here, 2 here, 3 here. I now compose it with reflection in the line y equals x. That's K transpose. And then I define K hat to be the average of K and K transpose. Okay? And the theorem is that if you compute the average displacement, but you replace Rn, the BCZ cocycle was this roof function whose average is like pi squared over 3, or the average on the periodic orbit is actually n squared over an. If you replace the BCZ cocycle, which appears in the Riemann hypothesis characterization, with K hat minus 3, then you not only prove Riemann hypothesis, you prove something much stronger. Okay, and so that's the main result. The proof. So we refer to K hat minus 3 as the discrete cocycle. We've changed the problem. K is an integer value function, and K hat is like a half integer value function. And actually, the difference between this function and Rn, they are bounded in L infinity norm. Okay, they're bounded distance from each other, so they're essentially indistinguishable. Now, we actually tried to prove Riemann hypothesis for quite a while and weren't able to do it. And the fact that we were able to get this was because we had an identity. And we discovered this identity ourselves independently But it turns out that this was already known to Hall and Cheung. It says that if you take k minus 3 and you sum this over any periodic orbit, this is equal to minus 1. It's not hard to prove. You can prove it by induction. But it's just, oh, why do you have such an identity? Well, if you play with this, you will discover stuff like that. Okay, there's a whole set of fixed points here where y equals x. And these fixed points, if you compute k equals 3, the periodic orbit has period 1. It's 2 minus 3, it's minus 1. Okay. There's another set of, so this is these are periodic orbits. Maybe I'll make periodic orbits red here. Here's another periodic orbit. It looks like this. So it's like 1, it goes to the 1 and then it goes to 4. 1, 4 is period 2. Okay? And so if you take 1 plus 4 minus 3, you minus 3 2 times, you get minus 1. Okay, so it's an identity. So this is the main ingredient, which allows us to do this. And using this, Yiming is able to show that if you take k hat minus 3 and you sum it over anything, so there's a concept of excursion, which I'll introduce briefly. It's a generalization of a periodic orbit. If you sum k hat minus 3 over any excursion, we can write down a formula for it. Almost a formula. So it's something like excursions, there's this notation for excursions, a over b, these are real numbers, plus b over a minus 3, plus epsilon, and epsilon is a number whose absolute value is less than 1. Okay? Now this is really amazing, but it comes from the fact that we have an identity like this. Your excursion could be very long. It could have like order n squared terms, many, many terms. And you're really getting all this cancellation because it's basically just controlled by some information and then up to some error. So that's those are the ingredients in the key ingredients. I might mention this fact here is related to an identity involving Dedekind sums that appears in the paper of Hall and Cheung, which is attributed to Zaharescu. So I don't know how Zaharescu got involved in this, but so Yiming kind of rediscovered as this similar thing. But I don't know anything about Dedekind sums. Okay, so let me tell you what is an excursion. So an excursion is a finite BCZ orbit. So you take an orbit in here, a finite orbit. With the property that the first and last point is to the left of all the other points. So you have to start from the left, you have to do something on the right, and the last point should also be to the left of everything on the right. That's an excursion. And a periodic orbit, if your period is AN, is an excursion of length AN plus 1. Okay, because you have to, the first point and the last point, you should think of them as different in the excursion. That's just a minor point, but essentially, you should think of excursion as a generalization of a periodic orbit. And here's a lemma. Again, this is one of these things where the proof is only a few lines. but using these correspondences, there's a one-to-one correspondence between BCZ excursions and the unit square, like this. This is a bijection, which is hard to explain, but it's an easy fact. And the bijection is given by, it sends this finite orbit to the first and last x coordinate. So we have a moduli space of all excursions. And this is an important object. The moduli space of all excursions has a nice subset, which is the collection of sub-excursions of the periodic orbit you should think of these as like the rational points inside the moduli space. So it's kind of like we have an integral structure, we have the main space, and Riemann hypothesis is like a statement about sub-excursions. So this statement here is enough to give you. So this is the key result in Yiming's thesis, which allows you to prove this strong form of the variant of Riemann hypothesis. Okay, so it's a statement that for any excursion, this estimate holds, and A over B is just a ratio of the x coordinates of the beginning and end. As you can see, most of everything that I'm saying here, it doesn't use any sophisticated ideas. It's very elementary. I should mention that with Andrew Best, we kind of check. Oh, my time is up. That's telling me. Okay. With Andrew Best, we can, if we replace this with, we want to do Riemann hypothesis. If we knew that this is like n to the p, that let's say O of n to the p, this should imply over here we would have O n to the p, and we're pretty confident about that. It's not complete. It's not written down, but it's something that we know. And yes, so these sub-excursions are in one-to-one correspondence with something called unimodular intervals. So I think I'm out of time. There is a geometric interpretation of Rn, which I don't have time to get into. But all these ideas put together suggest that, so I guess one final thought is that we didn't try to approach Riemann hypothesis. This characterization of Riemann hypothesis was known to me and Athreya more than 10 years ago, but we didn't take it seriously until maybe recently, or I didn't take it seriously until recently. And in the spirit of Children's College, I think if we cannot, if we don't have a strong reason to believe why something can't work, then I think we have to explore it. And so I want to encourage, especially our children students, to follow this line of investigation. So thank you for your attention.
Okay, thank you. Are there any questions from the audience?
Thank you for your talk. I wonder that can we study the Poincare section of the horocycle for the congruence surface, just the hyperbolic surface coefficient for the congruence group?
Yes, some work has been done in that direction. They didn't do congruence groups. I think gamma 2 has been done, but there are some other more interesting. There are some more interesting subgroups from the point of view of these methods of dynamics. So they come from translation surfaces. So we want to think of G mod gamma as the moduli space of some structure, and then use that structure to analyze the objects. So, but in principle, you could do G mod gamma for any lattice gamma. And something that I want to start is that how do you systematically, if you're given a congruent subgroup, or maybe not even necessarily even a congruent subgroup, but how do you kind of reconstruct the dynamics on the moduli space and reconstruct what is it the moduli space of? You just have a G mod gamma, but you don't understand how to see it as the moduli space of some geometric structure. And so the difficulty in those situations is that there's no natural correspondence. So most of the examples that are known, there's examples of square tile surfaces. These are not congruent subgroups usually. And then there are many other interesting kinds of, these are called Veitch groups. These are affine symmetry groups of translation surfaces, which are lattices in SL2R. And for many of those examples, a lot of these ideas can be extended very readily, including, for example, weak mixing of the return map. That kind of stuff should be readily provable.
Thank you.
Any other questions?
The epsilon in equation 2 is arbitrarily small or a fixed number?
The epsilon depends on the excursion. Yeah, but it's small. It's only at most 1, so that's not too bad. Yeah.
Can it be arbitrarily small?
Arbitrary small. Certainly. I mean, it could be 0. When you have a periodic orbit, this is 0. So you see this as a generalization of this. See, a periodic orbit is when A equals B. And when A equals B, you will get -1, and epsilon is 0. So there you go. So basically, you have a periodic orbit. It starts here and it comes back, but this is like a piecewise constant function. So if you perturb this periodic orbit a little bit, it doesn't change this identity. And so that's really where this comes from. This epsilon is not the exponent. No. I call it delta if you want.
Any other questions?
Another question that for this BCZ maps, can we prove for the standard conjecture for this setting?
That's a great question. I've been asking that question. I want some student to do this. You see, BCZ is very, very special. It's kind of like Gauss map for the horocycle flow. So people, when they Sarnak conjecture, it's a statement about. It's a very interesting conjecture, and but people usually try to prove Sarnak conjecture for various classes of dynamical systems. It would be very interesting for this one dynamical system, prove or disprove Sarnak. And I would guess you would disprove it, but yeah. Sarnak's conjecture is a statement about zero entropy systems. This is a zero entropy system. You don't have any work to do there, okay? So the question is just, can you study it? So it involves the Mobius function. And then I would take a symbolic version of the BCZ. You can encode it using the itinerary. And so you have a symbolic version. You have a compact metric space. You don't have to worry about this not being compact. Or you can make a compact version of the BCZ. And whether or not that satisfies Sarnak conjecture, I think it's a very intriguing question. And I don't know how hard it is, but it's worth looking into.
Thank you.
Great question.
Okay, so let's thank Yitwah again for a great talk.
Thank you.